Welcome to Bite-Sized Data Science. In the previous video, video 44, we learned about latitude and longitude and how to display spatial data in a notebook. It's time to dig a little bit further into it. Briefly, we saw that longitude and latitude are angles that uniquely identify a point on a sphere. Our reference point, 0, 0, is at the equator latitude and follows the Greenwich longitude, or more precisely, the Royal Observatory in Greenwich. With this coordinate system, we can have coordinates, for example, for Rome, New York, Sydney, and Chicago. The numbers here are qualified with north, south, east, and west. Remember the longitude and latitude we saw in video 44? We had positive and negative numbers, no north, south, east, and west qualifications. This is because the convention is to look at angles from minus 180 to plus 180 degrees from south to north and west to east. Why do we care about these types of measurements? Why don't we simply use a flat map? There are issues with a flat map. Here are some examples of issues. We learned a long time ago that the shortest distance between 2 points is a direct line. When it comes to projecting a sphere onto a flat map, you have edge issues where, for example, you would go west to go from Sydney to Honolulu, since there are no other path, but with a sphere, you can go east and get there much faster. The second problem is that as you go away from the equator, the shortest distance between 2 points is not necessarily a straight line. Going over either the North or South Pole can actually be shorter. Finally, there is an issue of perception. Take Greenland, for example. It has an area of 836,000 square miles. Compare that to Australia, that is over 3.5 times larger with 2.94 million square miles, but we are left with the impression that it is smaller. What about the United States? It is 3.8 million square miles, 4.5 times bigger than Greenland. You would not think that looking at this map. Okay, at this point you should be convinced that projecting on a flat map does not work well, except when dealing with a relatively small area. There is another thing we need to know related to longitude and latitude. In basic geometry, you can calculate the distance between 2 points on a sphere using the difference in angles and the radius. The problem we have is that the Earth is not a sphere, but instead is a spheroid. A sphere is perfectly round, so the radius is constant. For the Earth, the radius is not constant. To accommodate this, multiple coordinate systems were created. Think of a coordinate system as another type of projection. If you hear about coordinate systems or spatial reference systems, this is what it is about. I don't think you need to know more about this at the moment. Just keep in mind that there are different views of the Earth that will give different coordinates. Let's get into a notebook to demonstrate the issue with angle distances. I am using the IBM Watson Studio environment to run my notebook. If you are interested, you can find a link in the description on how to create a free account on that platform. Links to the notebook I'm using here are also available in the description. I'm using a library called GeoPy. It is part of my runtime environment. If it is not there for you, you can simply install it using a pip command. I created multiple points, 3 around the equator and 3 much more north. I want to calculate the distance of 1 degree in one direction or another. Here are the results. We see that a 1 degree longitude distance on the equator is over 17 times larger than the one much more north. We also see a difference in latitudinal differences. All this to say that you should make sure to use an appropriate library to calculate distance between 2 points. We're making progress on our spatial knowledge. We know that spatial is spelled with a T. We also know that flat maps representation can be deceptive. Finally, we understand that distances in degrees vary depending on the location of the points on the Earth. That gives us a good foundation to continue our journey into the spatial world. See you next time on Bite-Sized Data Science, and don't forget to subscribe.